Hello everyone, welcome to the seventh lecture of AAE 301. In today's lecture, we will be talking about the Laplace transform. And in particular, we will review the definition of the Laplace transform and go through the Laplace transform of some common functions as well as some useful properties of the Laplace transform. Okay, let's first review the definition of the Laplace transform. So the Laplace transform is an operation that maps a function in the time domain to a function in the complex domain. And the Laplace transform of a function g of t is given by the integral of e to the negative st times g of t from 0 to infinity with respect to t. And here we let g of s to denote the Laplace transform of g of t, and we let the symbol L to denote the Laplace transform operator. And here I like to point out that for this Laplace transform to exist, the function g of t has to be of exponential order. Basically, that means the magnitude of g of t has to be bounded above by an exponential function. So here, let's look at whether this function cosine t is of exponential order. And to do this, we first look at the magnitude of cosine t, and it's going to be this red line shown here. And you can see that the magnitude of cosine t is always bounded above by this exponential function e to the 0.1t. So this means that cosine t is of exponential order, and the Laplace transform of cosine t exists. Now, if you like to see how the Laplace transform works in the complex domain, I will suggest you to go to this YouTube video with the title called "What Does the Laplace Transform Really Tells Us? A Visual Explanation Plus Applications." And in this video, it will show you how this transform works in the complex domain. Now let's take a look at an example. So in this example, we will be looking at this function g of t, and this function takes value 1 when t is in this interval from 0 to t0, and this function takes value 0 when t is not inside this interval. And if you plot this function, it's going to look like this. So you can see the function has a value of 1 when t is in between this interval, and the function will have value 0 when t is outside this interval. So now let's take a look at how we can compute the Laplace transform of this function. And so first, we will follow the definition of the Laplace transform. So we will be looking at the integral of e to the negative st times g of t from 0 to infinity with respect to t. And this integral can be broken down into two parts. The first part will be this integral from 0 to t0, and the second part will be this integral from t0 to infinity. And we know that g of t takes value 0 in this interval, so we can ignore this term. And if you work out the integral of this first term, what you will get in the end will be 1 minus e to the negative st0 over s. And this will be the Laplace transform of this function. And before I move on to talk about the Laplace transform of some common functions, here I would like to share with you a very important property of Laplace transform, which is the linearity property. So basically, this means that the Laplace transform is a linear operator. And so for any two functions, f of t and g of t of exponential orders, the Laplace transform of the linear combination of f and g will equal to the linear combination of the Laplace transform of these two functions. So that's why we will have the Laplace transform of alpha f times plus beta g equals to alpha times the Laplace transform of f plus beta times the Laplace transform of g. And here, let's go through the proof together. So here we look at the Laplace transform of alpha f plus beta g, and by definition, it's equal to the integral of e to the negative st times alpha f plus beta g from 0 to infinity with respect to t. And we can break this integral into two parts. So here we will have the integral of e to the negative st times alpha f from 0 to infinity with respect to t, plus the integral of e to the negative st times beta g from 0 to infinity with respect to t. And because alpha and beta are constants, so we can take them outside of the integral. And if you look at this integral now, you will see that this is just the Laplace transform of f. And if you look at this integral here, you'll see that this is just the Laplace transform of g. So that's why in the end, we are left with alpha times the Laplace transform of f plus beta times the Laplace transform of g. Okay, now let's take a look at the Laplace transform of some common functions. The first function that we will be looking at will be this exponential function e to the at. And here a is a complex scalar. The Laplace transform of e to the at will be 1 over s minus a. And let's see how we can get this. So first, we again follow the definition of the Laplace transform. So here we will have the integral of e to the negative st times e to the at from 0 to infinity with respect to t. And we can combine these two exponential functions into one, and we will get e to the negative s minus at. And now we will work out this integral, and what you will get in the end will be negative e to the negative s minus at over s minus a, and t is evaluated at 0 and infinity. So here I like to point out that this integral only exists if s does not equal to a, because otherwise you will be having something non-zero divided by 0. And now if you expand this, you will get e to the 0 minus e to the negative s minus a times infinity over s minus a. And here, when the real part of s minus a is greater than 0, then this term here will converge to 0 as t goes to infinity. And so that's why in the end, we will be left with 1 over s minus a. Now, the second function that we'll be looking at will be this unit step function, 1 plus t. And the Laplace transform of this unit step function will be 1 over s. So before I dive into the derivation of the Laplace transform of this unit step function, let's first take a look at what the unit step function looks like. So the unit step function 1 plus t is a function that takes value of 1 when t is greater than 0 and takes value of 0 when t is smaller than or equal to 0. And if you plot it out, it's going to look like this. So the function value will be 1 when t is greater than 0, and the function value will be 0 when t is smaller than or equal to 0. And here you can see that this unit step function is actually e to the 0t. And so we can simply apply the result that we have obtained in the previous example to see the Laplace transform of this unit step function is actually just going to be 1 over s minus 0, and that's going to be 1 over s. Now, the third and the fourth function that we will be looking at will be the sinusoids cosine of omega t and sine of omega t. And the Laplace transform of cosine of omega t will be s over s squared plus omega squared, and the Laplace transform of sine of omega t will be omega over s squared plus omega squared. And here omega is a real scalar. So now let's look at how we can derive the Laplace transform of cosine of omega t. First, let's recall that cosine of omega t can be expressed as e to the negative I. Let's recall that cosine of omega t can be expressed as e to the I omega t plus e to the negative I omega t over 2. Then by the linearity of Laplace transform, we know that the Laplace transform of cosine omega t can be expressed as 1/2 times the Laplace transform of e to the I omega t plus 1/2 times the Laplace transform of e to the negative I omega t. And because we already know what the Laplace transform of an exponential function looks like, here we can directly apply the result that we have obtained before. So the Laplace transform of e to the I omega t will equal to 1/s plus I omega, and the Laplace transform of e to the negative I omega t will equal to 1/s minus I omega. Now we can then combine these two terms together, and in the end, you will see that the Laplace transform of cosine of omega t will equal to s/s squared plus omega squared. And similarly, for sine of omega t, we know that it can be expressed as e to the I omega t minus e to the negative I omega t divided by 2i. And so if you follow the similar procedure as we have done just now, you will be able to obtain the Laplace transform of sine of omega t as omega over s squared plus omega squared. Okay, now let's take a look at an example to see how we can apply what we have learned. In this example, we will look at this function g of t, which equals to 6 minus 3 times e to the negative 2t plus 2 cosine of 4t minus 3 sine of 6t. And now let's see how we can derive the Laplace transform of this function. So the Laplace transform of g will equal to the Laplace transform of 6 minus 3 e to the negative 2t plus 2 cosine of 4t minus 3 sine of 6t. And by the linearity of the Laplace transform, we know that this equals to 6 times the Laplace transform of 1 minus 3 times the Laplace transform of e to the negative 2t plus 2 times the Laplace transform of cosine of 4t minus 3 times the Laplace transform of sine of 6t. And we know the Laplace transform of 1 equals to 1/s, and the Laplace transform of e to the negative 2t equals to 1/s plus 2, and the Laplace transform of cosine of 4t equals to s/s squared plus 4 squared, and the Laplace transform of sine of 6t equals to 6/s squared plus 6 squared. So in the end, you will get the Laplace transform of g equals to 6/s minus 3/s plus 2 plus 2s/s squared plus 16 minus 18/s squared plus 36. And for the fifth function, we will look at the function t to the power of n, and n here is a non-negative integer. And the Laplace transform of t to the power of n will equal to n factorial over s to the power of n plus 1. To see this, we will have to rely on proof by induction. So we first look at the base case where n equals to 0. And when n equals to 0, t to the power of n equals to 1, and the Laplace transform of 1 equals to 1/s. And next, we look at the induction step. And first, we will assume that the Laplace transform of t to the power of n equals to n factorial over s to the power of n plus 1 is true for some n that is greater than or equal to 0. Then we check if the Laplace transform of t to the power of n plus 1 also follows this form. So to see this, we first follow the definition of the Laplace transform. So the Laplace transform of t to the power of n plus 1 equals to the integral of e to the negative st times t to the power of n plus 1 from 0 to infinity with respect to t. And this integral can be broken down into two parts by integration by parts. And you will see the first part will just be 0 under the assumption that the real part of s is greater than 0. And for the second part, you will see that this integral right here is actually just the Laplace transform of t to the power of n. So we will be left with n plus 1 over s times n factorial over s to the power of n plus 1. And that's going to give us n plus 1 factorial over s to the power of n plus 2. And so you can see that the Laplace transform of t to the power of n plus 1 also follow this form. So this implies that the Laplace transform of t to the power of n will just be n factorial over s to the power of n plus 1. Now the sixth function we will be looking at will be this type of function with the exponential function e to the at in the front of a general function g of t. And the Laplace transform of this type of functions will be a shifted version of the Laplace transform of g of t. Essentially g of s minus a, and here a is the scalar in the power of the exponential function. And now let's see how we can derive this. So first, we follow the definition of the Laplace transform, and we will get the integral of e to the negative st times e to the at times g of t from 0 to infinity with respect to t. And next, we will introduce a new variable called x prime, which equals to s minus a. And so this expression here can be rewritten as the integral of e to the negative s prime t times g of t from 0 to infinity with respect to t. And you see that this is actually just the Laplace transform of g of t evaluated at s prime. And because we know that s prime is going to be s minus a, so in the end, we see that the Laplace transform of e to the at times g of t is just the Laplace transform of g of t evaluated at s minus a. And now let's take a look at an example. In this example, we will look at this function g of t, which equals to 2 times e to the negative 3t plus 4 times e to the negative t times t squared plus 6 times e to the power of 3t times cosine of 2t minus 3 times e to the negative 2t times sine of 4t. And we apply the Laplace transform to g of t, and we will get 2 times the Laplace transform of e to the negative 3t plus 4 times the Laplace transform of e to the negative t times t squared plus 6 times the Laplace transform of e to the 3t times cosine of 2t minus 3 times the Laplace transform of e to the negative 2t times sine of 4t. And the next thing we do is let's recall that the Laplace transform of 1 will equal to the Laplace transform of the unit step function, and that's equal to 1 over s. And the Laplace transform of cosine of 2t will be s over s squared plus 2 squared. And the Laplace transform of t squared will be 2 factorial over s to the power of 3, and that's equal to 2 over s cubed. And the Laplace transform of sine of 4t will equal to 4 over s squared plus 4 squared. And because we know that the Laplace transform of e to the at times g of t will equal to g of s minus a, so this means that the Laplace transform of e to the negative 3t will equal to the Laplace transform of e to the negative 3t times 1. And so this will give us 1 over s plus 3. And the Laplace transform of e to the negative t times t squared will give us 2 over s plus 1 cubed. And the Laplace transform of e to the 3t times cosine of 2t will give us s minus 3 over s minus 3 squared plus 2 squared. And the Laplace transform of e to the negative 2t times sine of 4t will equal to 4 over s plus 2 squared plus 4 squared. And so that's why in the end, we see that the Laplace transform of g of t will equal to 2 times 1 over s plus 3 plus 4 times 2 over s plus 1 cubed plus 6 times s minus 3 over s minus 3 squared plus 2 squared minus 3 times 4 over s plus 2 squared plus 4 squared. Now for the seventh function, let's look at the delta Dirac function or the impulse function delta of t. and the Laplace transform of the delta Dirac function is equal to 1. First, let's take a look at what the delta Dirac function delta of t looks like. So the delta Dirac function is a function that is positive infinity at the origin and is 0 everywhere else and has an area of 1. And to help you visualize the delta function, let's take a look at the function delta n of t, which is an approximate of the delta Dirac function. So the function delta n of t is a function that takes value n when t is inside the interval from 0 to 1 over n, and it takes value of 0 when t is outside the interval. And if you plot it, it's going to look like this. So you can see delta n takes value of n when t is in between 0 and 1 over n, and it takes value 0 when t is outside the interval. And if you look at the area of this function, you will see that the area is just this rectangle here, and the area of this rectangle is n times 1 over n, which equals to 1. And this holds for any positive n. And now, if you let n approaches to infinity, you can see that the value of delta n will approach to infinity, and the interval gets smaller and smaller, and in the end, it will just be 0. So you can see that if you let n goes to infinity, then delta n will approach the delta Dirac function that we are interested in. Now, before I move on to talk about the derivation of the Laplace transform of the delta function, here's another property of the delta function that I would like to share with you. So if you look at the area of the product of h of t and delta t, then that area will equal to h of 0. And now I'm going to show you how you can derive this. So first, we are going to express the delta function as the limit of delta n as n goes to infinity. So this integral here can be rewritten as the limit of the area of the product of h and delta n t as n goes to infinity. And now let's take a look at how we can evaluate this integral. For this integral, we only have to look at the interval from 0 to 1 over n, because we know that the function delta n t takes the value n when t is inside this interval, and it takes value 0 when t is outside the interval. And here we know n is a constant inside this integral, so we can take this out of the integral. And what we'll be left with will be n times the integral of h of t from 0 to 1 over n with respect to t. And now we are going to approximate this integral with h of 0 times 1 over n. And as we let n approaches to infinity, this approximate will get better and better. And in the end, you can see that what we'll be left with is just going to be n times h of 0 times 1 over n. And here, n times 1 over n cancels out each other. So in the end, we will be left with h of 0. And now I'm going to show you how you can apply this property to derive the Laplace transform of the delta function. So first, by definition, the Laplace transform of the delta function will equal to the integral of e to the negative st times delta t, and from 0 to infinity with respect to t. And this is actually just going to be the area of the product of e to the negative st and delta t. And so according to the property that we have just derived, we know that this area will equal to e to the power of negative s times 0, and this is 1. So that's how we can derive the Laplace transform of the delta Dirac function. Now, let's talk about some useful properties of the Laplace transform. The first property we will look at is the differentiation property. So if you look at the Laplace transform of the first derivative of the function g of t, it's going to equal to s times the Laplace transform of g minus g of 0. And to see this, let's just follow the definition of the Laplace transform again. So the Laplace transform of the first derivative of g will equal to the integral of e to the negative st times the derivative of g from 0 to infinity with respect to t. And here we can apply the integration by parts to get these two terms here. And if you work out each of these terms, you can see that in the end, you will be left with s times the Laplace transform of g minus g of 0. And that's how you can get the Laplace transform of the first derivative of the function g. And now let's take a look at the Laplace transform of the second derivative of the function g. And that's equal to s squared times the Laplace transform of g minus s times g of 0 minus the first derivative of g evaluated at 0. So to obtain this result, we can first let g1 to denote the first derivative of g, and we can see that the first derivative of g1 will be the second derivative of g. And now we want to compute the Laplace transform of the second derivative of g. It's going to equal to the Laplace transform of the first derivative of g1. And according to the result that we have just obtained, we know that this is going to equal to s times the Laplace transform of g1 minus g1 of 0. And because we know that the Laplace transform of g1 is going to be the Laplace transform of the first derivative of g, so we know the Laplace transform of g1 will equal to s times the Laplace transform of g minus g of 0. And now we substitute this back into the expression above, and in the end, we will get the Laplace transform of the second derivative of g, and that's going to be s squared times the Laplace transform of g minus s times g of 0 minus the first derivative of g evaluated at 0. And as you can imagine, you can apply the same trick to obtain the Laplace transform of the nth derivative of g. And in the end, you will get this general expression shown here. Now let's take a look at the second property of the Laplace transform, the integration property. For this property, we will look at the Laplace transform of the integral of a function, say g. And here we're going to call this integral h. And by definition, we know that the first derivative of h will be g. And so when we look at the Laplace transform of g, it's going to equal to the Laplace transform of the first derivative of h. And now, according to the differentiation property, we know that this will equal to s times the Laplace transform of h minus h of 0. And here, h of t is defined as the integral of g of tau from 0 to t with respect to tau. So h of 0 will be the integration of g of tau from 0 to 0 with respect to tau. And so we know this is going to be 0. So in the end, we will be left with s times the Laplace transform of h. And so this implies that the Laplace transform of h is going to be the Laplace transform of g over s. And here I would like to show you a comparison between the two properties that we have just talked about. When we look at the Laplace transform of the first derivative of g, what we will get in the end is s times the Laplace transform of g minus some constant g of 0. And when we look at the Laplace transform of the integral of the function g, what we will get in the end will be the Laplace transform of g over s. So this means that when you want to compute the Laplace transform of the derivative of a function, you basically just multiply s to the front of the Laplace transform of that function. And when you want to compute the Laplace transform of the integral of a function, you basically divide the Laplace transform of that function by s. Now let's take a look at an example. Here, we want to find the Laplace transform of the integral of sine of omega tau. And if we work out this integral, you will see that this equals to 1 over omega minus cosine of omega t over omega. And then we can apply Laplace transform to this expression, and in the end, we will get omega over s times s squared plus omega squared. And you can see that this is essentially just the Laplace transform of sine of omega t over s. Now let's take a look at the third property of the Laplace transform, the convolution property. First, let's review what a convolution is. So the convolution between two functions g and u is defined as follows. So the convolution between g and u is going to equal to the integration of g of t minus sigma times u sigma from 0 to t with respect to sigma. Similarly, the convolution between u and g is equal to the integration of g of t times u of t minus sigma from 0 to t with respect to sigma. And notice that the convolution between g and u is essentially equal to the convolution between u and g. Now let's take a look at the Laplace transform of the convolution between g and u. So first, let's follow the definition of the Laplace transform, and we will see that the Laplace transform of this convolution will equal to the integration of e to the negative st times the convolution between g and u from 0 to infinity with respect to t. Now, we replace this expression here by the definition of the convolution. So we will get the integration of e to the negative st times the integration of g of t minus sigma times u sigma from 0 to t with respect to sigma, and from 0 to infinity with respect to t. And here I'm going to multiply the e to the negative st into this integral. So here we will have a double integral in the front, and the integrand will be e to the negative st times g of t minus sigma times u of sigma, and we integrate with respect to sigma first and then with respect to t. And the next thing I'll do is I will change the order of integration. So first, let's see what we're doing here. In this expression, we are integrating sigma first from 0 to t, and then we integrate t from 0 to infinity. And you can actually visualize this by drawing a plot shown here. So for the horizontal axis, we have t, and for the vertical axis, we have sigma. And this line here is a line for t equals to sigma. And for this integration, what we're doing is we are integrating sigma from 0 to t, and then we integrate a t from 0 to infinity. So essentially what we are doing is we're integrating over this area here. Now, as you can imagine, in order to integrate over this area, there's another way we can do this. So that way is going to be we integrate t from sigma all the way to infinity, and then we integrate sigma all the way from 0 to infinity. So after changing the order of integration, what we'll be left with is going to be this expression here. So here we will have the integration of e to the negative st times g of t minus sigma times u of sigma, and from sigma to infinity with respect to t, and then from 0 to infinity with respect to sigma. And after we change the order of integration, we see that this u of sigma is a constant inside this integral with respect to t. So we can take it out of this integral, and we will get this expression in the end. And next, we will introduce a new variable called t prime, and t prime is equal to t minus sigma. And according to this definition, we know that t will equal to t prime plus sigma, and dt will equal to dt prime. In addition, when t is sigma, t prime is equal to 0, and when t is infinity, t prime is also equal to infinity. So here, after introducing t prime into this expression, what we'll get in the end will be this expression here. And you can see now the integration range is from 0 to infinity, and the integrand becomes e to the negative s times t prime plus sigma times g of t prime time with respect to t prime. And the next thing we can do is we can break this exponential term into two terms, e to the negative st prime times e to the negative s sigma. And again, e to the negative s sigma is a constant inside this integral with respect to t prime, so we can take it out of this integral. And what we will be left with in the end will just be this integral here. So this integral is the integration of e to the negative s t prime times g of t prime with respect to t prime. And you can see that this is essentially just the Laplace transform of g. And this Laplace transform of g has nothing to do with sigma, so we can again take it out of the integral, and what we'll be left with inside the integral will just be the integration of e to the negative s sigma times u of sigma from 0 to infinity with respect to sigma. And again, you see that this is essentially just the Laplace transform of u. So in the end, we see that the Laplace transform of the convolution between g and u will be the Laplace transform of g times the Laplace transform of u. And now let's look at an example to see how we can apply this property. In this example, we will be looking at the convolution of e to the negative t and e to the negative 2t. And by the definition of the convolution, we can show that in the end, it's going to equal to e to the negative t minus e to the negative 2t. So when we apply Laplace transform to this expression, we see that it will equal to 1 over s plus 1 minus 1 over s plus 2. And this is actually equal to 1 over s plus 1 times 1 over s plus 2, which is the Laplace transform of e of negative t times the Laplace transform of e to the negative 2t. Now let's take a look at the last property of the Laplace transform, the shifting property. For this property, we will look at how we can derive the Laplace transform of a delayed copy of a function g. So to help you understand better, let's take a look at this graph. So here we have a function g, and this function takes value 0 when t is smaller than 0, and it can take any arbitrary value when t is greater than 0. And now we delayed this function by some time t0, and so here you see this green line. This is essentially the delay copy of g of t. So now let's take a look at the Laplace transform of this delay copy. First, by the definition of the Laplace transform, this will equal to the integral of e to the negative st times a g of t minus t0 times a delayed copy of the unit step function. And because there is a delayed unit step function, we can simply ignore any t that is before t0 in this integration. And what we'll be left with is going to be this integral of e to the negative st times g of t minus t0 times 1 from t0 to infinity with respect to t. And next, we will introduce a new variable again called t prime, and t prime here is t minus t0. And by this definition, t will equal to t prime plus t0, and dt will equal to dt prime. And also notice that when t equals to t0, t prime is 0, and when t equals to infinity, t prime is infinity. After introducing this new variable, we can rewrite this expression here as this expression below. So here we will have the integration of e to the negative s times t prime plus t0 times g of t prime from 0 to infinity with respect to t prime. And again, we will break this exponential term into the product of two terms, e to the negative st prime and e to the negative st0. And because e to the negative st0 is a constant inside this integration, we can take it out of this integration. And what we will be left with in the end will be the integration of e to the negative st prime times g of t prime from 0 to infinity with respect to t prime. And you will see that this term here is just the Laplace transform of g. And so we see that the Laplace transform of the delay copy is just going to be e to the negative st0 times the Laplace transform of g. And now let's take a look at an example to see how we can apply this property. In this example, we will be looking at the Laplace transform of the delay copy of the delta function. So here, notice that this delay copy can be rewritten as delta of t minus t0 times a delayed copy of the unit step function. And then according to the property that we have just derived, we know that this will equal to e to the negative st0 times the Laplace transform of the delta function. And we know that the Laplace transform of the delta function equals to 1. So in the end, we will be left with e to the negative st0. Okay, this is the end of today's lecture, and I hope to see you in the next one.